All right, good morning. We'll start our little review part of this morning here now. Is there any questions I can take from the room before getting into some questions in our packet? If you have follow-ups on anything, just let me know throughout here. This is the chapter 1 to 2 review questions packet that's up on Carbon and lecture slides. It's where you would find chapters 1 and 2 notes. Later today, once we start the lecture portion, probably around 8:05, 8:10-ish, we'll get into chapter 3 and get a start there. There's a few details in chapter 3, I think, that will reinforce a few parts of chapter 2 or hopefully help make sense of, in particular, the atomic mass unit scale. So I think there are some aspects by pushing forward into chapter 3, but our test will only be through chapter 2. So this question here is getting at the diagrams depicting nitrogen with the black spheres, hydrogen with the white spheres. So it looks like ammonia molecules, though ammonia really itself isn't on our nomenclature list. So this looks like it's depicting NH. There we go. It's depicting NH3 molecules. And so we see 4 of them in the box. And so what words apply here, and then we can think about what the words mean. Uniform throughout means that if I look at the mixture, that it appears to be randomly mixed, that there's not one side of the box that has one thing, another side of the box has another thing. So sometimes it's hard to depict randomness with only like 3 or 4 particles, but this box is just trying to depict the molecules in like random orientations. So that word would apply. Uniform throughout would be like if we did have more than 2 things, or if we did have more than one thing. So if we had 2 or more things in this box, that they were just kind of randomly oriented in the box. If you see all the one spheres on this side, all the other spheres on the other side, then that would be some sort of heterogeneous mixture. So uniform throughout is addressing homogeneous versus heterogeneous. And so you can be homogeneous without being a mixture. So we do have a word homogeneous mixture, but we can look at this box and say it appears homogeneous. Homogeneous just appears uniform throughout. 2 or more things, then we can say, is it a homogeneous mixture or just a pure substance or a pure element? So uniform throughout appears to be homogeneous, definitely not a mixture though. The non-variable composition is getting at, is it a mixture? So non-variable composition just means, do I see 2 or more different things in this box? I just see ammonia molecules. If I saw some other sphere, if I saw something that looked like this in the box and I had a second thing that looked like this, and that would be depicting N2, and that would be a second molecule, then that would be depicting a variable composition. Okay, so the box is shown here without that second molecule would be non-variable. So variable is 2 or more things, non-variable just one thing present in the box. So that is a non-variable composition. Is it a molecule? Is NH3 something that we call a molecule? It is. Anytime we have 2 or more atoms that are bonded together, that are stuck together, we call that a molecule. Now, if we had nitrogen as a different example, that's still a molecule. It could be the same element bonded together. So molecules can be one atom bonded with some other atom of any element type. If we had just something like helium, where we had just a single atom like this, that's not a molecule, of course. That's just a single atom. Okay, so molecule applies to the NH3s here, and then it's of course a compound. Compound is just 2 or more elements bonded together. So we see 2 elements bonded together, so that makes it a compound. So N2, this example here, would be not a compound, that would just be an element, or excuse me, that would just be a molecule. If it only contains the same element, then we could call it an element. So even though nitrogen exists as N2, we would still call an N2 molecule an element, because it only contains one element. So anything, no matter the count, that contains just one type of atom would be called an element. So if we saw sodium would be just a bunch of sodium atoms overlaying each other like side to side in front, because it's a solid at room temperature, and that would still be the elemental form or the element of sodium. Okay, so all these terms here for this particular box of ammonia molecules would apply. Let's do some sig fig problems. Now we're looking at numbers like 50 plus 74. Just imagine that 50 is some number that you're just interpreting to have just one sig fig. So you're interpreting the plus minus here to be plus or minus 10. Like that's what we mean by just having one sig fig. So we're just looking at 50 as having one sig fig plus 74 going to 124, but I need to round to the greater quantity placeholder. So the tens placeholder is a greater quantity than the ones placeholder, so I round this to that second significant figure to the 2's placeholder of 124, so I'd round that to be 120 with 2 sig figs. If we want to go ambiguous, we might say 100 or 1.2 times 10 to the 2 to go to scientific notation. I don't think you're going to have to report answers numerically on the test using scientific notation. You know how sometimes in lab and LabWrite you have to enter scientific notation? I don't think you'll have to do that at any point on the exam. Any number you enter on the test would just be a normal number. Yeah. The higher value placeholder. So it's good if we think of the plus minuses here, like the 74 is plus or minus 1 because it's good to the 1's placeholder. The 50's plus or minus 10. So it's this plus or minus 10 that's going to make the 120 vary in this placeholder here. Does that make sense? So addition and subtraction, we look for the greater value, the greater quantity placeholder. So think from left to right, the further to the left. Yep. Now the second question on this packet is 16.0 times 1.25 in parentheses. So let's do that first. That gives me, so this here works out to 20.0 to 3 sig figs because it's 3 sig figs times 3 sig figs. When we multiply, we count sig figs. And then we're going to divide by the sum of 1.25 and 3.75. No, 3 sig figs plus 3 sig figs, we're not counting sig figs, we're looking placeholders. So we're just looking for this here. So I get 0, 0, and that's going to be 5.00. And then all 3 of those digits being significant. So I should have 3 sig figs here because I'm looking at the placeholders. Both those values end in the hundredths place, so the 5.0 should be reported all the way to the hundredths placeholder, which therefore makes it have 3 sig figs. So 3 sig figs divided by 3 sig figs should be reported to 3 significant figures. So we would keep 3 sig figs on the 4. So sometimes we're adding zeros. If we just throw this into the calculator, if you just did this problem in the calculator, just say 4, then we have to interpret the uncertainties from the numbers in the problem to see it should be 4.00. And so it's all about just when you get a result, how good do we know? Like how precise do we know the result to? That's what sig figs are getting at. And so if we just said 4, that's not very precise. 4.0, a little bit more precise. 4.00 is the proper preciseness for the numbers in that second problem. Now the scientific notation math problem might be a little tricky. Let me go back to something I said earlier. You may have to know and use scientific notation on the test, but just not enter it, numerically into a problem as a numerical answer on the test. So when you have to enter a numerical answer, if you've looked at the Carmen practice exam, it has a couple numerical entry questions. That's what I'm kind of referring to. If you haven't looked at the practice exams yet, take a look at them because they'll show you and you'll take the exam in the same format you take the real exam, just so that you can see any special nuances with entering answers. The numerical entry problems are all just enter a number. So you're just going to enter the number that you see on your calculator without scientific notation. But now in this problem here, we might need to think about what the scientific notation means. If we just throw this into a calculator, we might make a mistake and lose the sig fig here. But let's write these two numbers out in their whole form. So 4.74 times 10 to the 4 would be 47400. And just to check, that would be 1, 2, 3, 4. So that would be 4.74 times 10 to the 4. And then let me write 7.87 times 10 to the 4 would be 78700, and then do the addition. So we're going to add these up. And again, it kind of comes down to placeholders. Let me switch colors here. So it's all about the placeholder. So we're going to round to that indicated placeholder. So I get 1261. And so if I'm reporting that in scientific notation, if I had to just report scientific notation, I'll go 1.261 times 10 to the 5. Now I could do it this way too, 12.61 times 10 to the 4. So the point here is, like, if you do see a sig fig problem with scientific notation, my recommendation would be just write the numbers out in their full form and get rid of the scientific notation. Then do the math, then apply the sig fig rule. If you have to go back to scientific notation to look for the right answer, then you can do that. Okay, so tricky example there at the bottom, just using scientific notation within a sig fig problem. Let's do a conversion problem. There's not a lot of conversion factors. If you haven't seen the practice exams or some of the announcements, there's an equation sheet you get with the exams that has a couple equations on it. I think just the one equation is actually just the sum for the average atomic weight, the sum over all fractions and the atomic weights of natural occurring isotopes. And you get a few conversion factors. Like, we could give you more conversion factors if you need them. If you recall, I said before, we only give you the equation sheet generally for the test that's written. And within questions, if you need a specific, like, non-scientific, non-SI conversion factor, we'll give that to you. For example, we don't expect you to have the centimeter to inch conversion memorized. We don't expect you to know how many feet are in a mile. If you need to use those conversions, we'll give those to you. So this problem here, there's really only one conversion factor that really you need to know that comes up a bunch in problems of volume, and that's just 1 cubic centimeter is 1 milliliter. So that's just one conversion factor that we expect that, a cubic centimeter is exactly a milliliter. That might help us in this problem here where we're trying to go from meter times meter into liters. And so if we want to make this conversion here in this problem, a few things we could do is we could just do the multiplication for the volume into cubic meters and then convert to cubic centimeters. But I think an easy starting point of this problem is to just convert the meters into centimeters, because there's just 100 centimeters exactly in 1 meter. Of course, I need to flip that other way around. So 1 meter is 100 centimeters. And so my 5.00 centimeter box would be 500 centimeters, 3 sig figs times 850 centimeters times 250 centimeters. So I can convert this to centimeters. Now, why might I do this? Why might I do this? Because then that'll just give me the quick conversion into milliliters and then a very easy conversion into liters from there. So the main conversions I need to know how to use are the prefix conversions, so like 100 centimeters in a meter, 1,000 millimeters in a meter. Those types of conversions using the prefixes are the ones that we want to make sure you know for chapter 1 here on midterm 1. So if I go 500 times 850 times 250, that gives me a volume. It's a big number. I'm going to switch to scientific notation mode on my calculator. So it says 1.0625 times 10 to the 8, and the units would be cubic centimeters. And of course, that would have 3 sig figs because I just multiplied 3 by 3 by 3 sig figs. Now, if we want to convert liters, which is what we're looking for here, because it says what's the volume of the pole in liters, then we just either do one of two things. We either go 1 cubic centimeter is 1 milliliter, and that's a very easy conversion, exact conversion. Or I could have just done this. I could have just said, well, why not just say that this would just be the cubic centimeters is just a milliliter, and just make that conversion right off the bat. So very easy conversion into milliliters. And then the last conversion I need to go to liters is just the milliliters into liters. And so there's 1,000 milliliters in a liter. So I just need to divide by 1,000. So that'll be 1.06 to go to proper sig figs times 10 to the 5 liters. Okay, so we'll see some numerical questions on the test. There's still multiple choice. A few of the numerical entry questions will require you to input an answer, and inputting an answer should just be more of an ordinary number. So we probably wouldn't give you a number like this to enter numerically. We'd give you an answer that goes to like closer to towards a whole number. If you do get a numerical entry question on the test, look to see the question. It'll always say report your answer to the nearest like 0.1 or 0.01 or the nearest whole number. Just enter the answer as indicated on the test. We're usually not testing sig figs on top of the actual question on the test. Just because you get this a lot in lab, you may be wondering from like LabRite versus the exam. The exam kind of has its own entry system. We're generally only asking sig fig questions on actual sig fig questions, and then the other exam numeric questions are just getting at inputting the right numerical answer and being where that answer is supposed to be. Let's talk about these experiments here, what I hope you remember from the important experiments at the start of chapter 2 that went into the discovery of sort of modern theory of atoms and elements. And so J.J. Thomson is the one credited with discovering the electron through the cathode ray tube experiment, the CRT cathode ray tube experiment. This is like late 1800s, just to put this. This is kind of like by timeline, the first experiment that we talk about. A date I did mention in class that I think is mentioned in chapter 2 that might be worth pointing out just to kind of get the lay of the land around the late 1800s is the periodic table was proposed in roughly 1870. So about 30 years after the periodic table was proposed, with a bunch of holes with only about 40 to 50 elements at that time being placed and kind of starting to be arranged, a few of them misarranged already, that was kind of where the electron's discovery was coming. So very early on in terms of the discovery of what made different elements different from each other, and really still only about half the elements at that point even known. And so that's the discovery of the electron. I know it also discovered the mass to charge ratio of the particle. If you recall, it made the particle was deflected by the magnetic field. That was how they determined that the particle had a charge. And then it was deflected towards the positive charge. That's how they knew it was negative charge. And so it depicted that and discovered that negative particle. It also discovered, or kind of was going after the idea that the atom was divisible. People thought the atom wasn't divisible, and this showed that you could divide an atom into smaller subatomic particles. And so the order of the discovery, I think this is just interesting just to make sure we see that the first particle discovered was the electron, then it goes the proton, then it goes the neutron in terms of the discovery of these subatomic particles. The neutron was discovered not even 100 years ago, which I think is just kind of fascinating to kind of think about that if we were in this room 100 years ago, which I think McPherson was built in like 1910, so this room existed over 100 years ago, that there would have been no discussion of what the neutron was 100 plus years ago. So kind of crazy to think about how modern some of these actual theories are that we're talking about, even though it seems you would probably think they're even older than what they are. Curie discovered some radioactive particles, or we can even mention, well, I guess it's down below. I'll wait till it's in the fourth question. Curie discovered that radioactive elements kind of had three main sort of particles or three main rays that could be detected. And so it detected the alpha particle, the beta particle, and then the gamma ray. And the gamma ray, this was the high voltage light. It was really high energy light, even higher energy than an X-ray. So it's like a photon of light. We'll talk about photons more in chapter 6, but high energy light in the form of a ray. And then the alpha particle was the helium nucleus. And then the beta ray was the electron. So it discovered the same type of particle that Millikan discovered and saw within the radioactive experiment. So radioactive substances are giving off electrons. They're breaking apart into smaller elements, later determined to be the helium nuclei, and then also giving off high packets of energy, gamma rays. And then I think one of the important parts of talking about Curie's work is to see that Rutherford used the alpha particle to shoot it at the thin gold foil. And so the gold foil showed that the atoms were accumulating their positive charge into a center. And that's the only way that they were deflecting those alpha particles. They expected the alpha particle to go straight through. If that plum pudding model were true, if all the subatomic particles, the protons, neutrons, which I didn't even know about yet, but they're just thinking, yeah, this light electron, where's the positive charge? It has to be some mass from the positive charge. If that's distributed where the atom is, then there should be no big center of mass that could deflect a particle, but they saw deflection, and that led to the nuclear discovery. So that Rutherford's experiment discovered the nucleus of the atom. Millikan's work discovered the mass and the charge of the electron. Millikan suspended atoms using gravity, so they would put charge on atoms and see how much of a magnetic field was required to suspend the particles within the magnetic field that allowed the discovery of the mass and the charge of the electron. So we get the mass and charge of the electron from Millikan. We get then the discovery of the nucleus from Rutherford. Let's talk about some quick naming, quick reviews. Is that I'm back to the iPad not linking up quickly as I'm changing slides. But if you're in the notes, it's just the next slide on naming. So the slide is getting at some ionic compound nomenclature. And remember, you just go cation name, then anion name. So sodium chloride for the first one. I think I'll just not write anything for this slide, and hopefully the pen will catch up here. As we get situated, but sodium chloride, magnesium chloride. So we don't need to call MgCl2 magnesium dichloride. The dichloride is understood from magnesium's periodic table placement being a 2+ ion. So sodium is in group 1, so it forms a plus ion, so it only takes 1 Cl- to pair up with it. Chlorine's in the halogen group, so it picks up the charge by adding just 1 electron. So we're looking at periodic table placement for our simple atomic ions. So the first group only form +1s, the second group only +2, the halogen group only -1s, the oxygen sulfur group -2s, nitrogen -3. So we're just looking at periodic table placement. And then CaO, calcium 2+, O2-, that's just calcium oxide. Sodium oxide, we don't have to call that disodium oxide. Remember, when we have that nomenclature system that we use for things like CO2, Cl4, that's for molecular compounds. So my first thought on these compounds would be classify a compound in naming as ionic or molecular. And if you see metal, non-metal, if you see left side, right side, periodic table, then that's going to be a ionic compound. We name it cation, anion name. And then we understand the charges based on periodic table placement. Or if it's a transition metal, we go Roman numeral system. One of the detail would be the far left side element of hydrogen is still a non-metal. So if you see HCl, HF, HNO3, that's an MC, that's a molecular compound. Even though it's left side, right side, it's hydrogen. So hydrogen's a non-metallic element. So when you see hydrogen in compounds with no no metal atom, then that's still a molecular compound. We're gonna name those things on the MC side. So like, it might be an acid, we'll name it as an acid. If it's a hydrocarbon, we'll name it as a hydrocarbon, etc. Magnesium nitride. So magnesium's a 2+. I'm just seeing if my pen's catching up. It's pretty far behind. N is a 3-. And so for that one there, so we're just pairing up our charges. And another thought could be that these charges were obtained from magnesium being neutral and losing its electrons and giving them to the nitrogen. And so if you've ever thought, like, how do we balance, or why are we balancing an atom to be neutral? It's because we want a neutral charge for Mgn when we write the formula, because all of the electrons that magnesium would have had gone on to the nitrogen and were accepted by nitrogen. So it keeps the actual number of electrons consistent with the elements that we have having a neutral charge. And so that's why we do this like cross multiply trick here to go to Mg3N2. When we write the formula, it would just be Mg3N2. And then all the electrons that magnesium would have had, those 2 extra electrons that it had lost, were given to the nitrogen. So if we just think magnesium has like 12 electrons times 3, nitrogen should have had, or nitrogen brings to the table 7 times 3 electrons, then we just like rearrange what those electrons are and kept them constant throughout the molecule. So that's why we want our molecule to be overall neutral in charge, so that we haven't created or destroyed electrons within the formula. And so just our check here, 6+, and then minus or plus the -6 goes to 0. So our check is 2+ times 3, 3- times 2, 6+, 6-, neutral in charge. So I'm just kind of getting at, like, why do we want the formula to be neutral? So that we haven't created or destroyed electrons within the compound. Ammonium sulfate. Ammonium is NH4+. Sulfate is SO4 2-. So we're going to need 2 of the 2+ to pair up with the 2-. And so then we write the formula. Obviously, I don't put the charges in the formula. So NH4,2SO4 would be the formula for ammonium sulfate. And then manganese 4 oxide would be Mn4+. So manganese 4 is indicating that charge. Oxide's a 2-. And so we just need 2 of the 2-. Now I don't cross multiply this. I'm just trying to balance the charges. When there's odd even, then I can cross multiply to quickly get the subscripts. Now when they're both even, or I'm just trying to figure out, the -4 plus 4, so I get MnO2. Now when we go even odd, like with manganese 5 oxide, I have a different compound where manganese has a 5+ charge. Then I can do my cross multiplying here, 10+, 10- for Mn2O5. Now, we don't expect you to know what are the charges common for a given element. We just want to go from name to formula, formula to name here in chapter 2. And then for our transition metals, we're using Roman numerals as part of their name. the next slide has some additional nomenclature. Again, if you're following the notes, my silly iPad screen is lagging. Maybe if I unmirror my screen and reconnect it seems to let it catch up. Okay, so the next one, sodium hydrogen phosphate. Now, the hydrogen phosphate ion is an ion of phosphate. So when you see something like hydrogen phosphate, that's an ion. That's where we've taken an H plus ion and added it onto PO4 3-, and then that kicks the charge down to 2- on the overall ion. So that makes HPO4 have a 2- charge because it just got dropped by 1 by adding the H plus. If we do it again, we get to H2PO4 with a minus. And if we do it a third time, we get to the acid H3PO4. So if we get all the way to this, then we get to our charge neutral molecular compound that we name as being an acid. So we name H3PO4 phosphoric acid. Now, since HPO4 2- still has a charge, we just keep that hydrogen phosphate as part of its name. And so sodium hydrogen phosphate, I would need to have 2 sodiums. Sodium's a plus, so I need to have 2 of the sodiums to pair up with the HPO4 2- ion. So 2- takes 2 2+ to pair up. So it would be Na2HPO4. I doubt we'll see even that hard of an example. That's probably one of the harder nomenclature examples that there are. So if we can answer that one, hopefully we're really prepared for what we'll see in the test. So that's a pretty tricky question, but just know hydrogen phosphate still an ion, just had H plus added to the phosphate formula. Chromium 6 oxide, that just means chromium 6+. And then sulfide is in the oxygen group, so it's a 2-. And so we just need 3 of the 2- to pair up, so this will be CrS3. CSO isn't the most common alkali metal, but it's in the alkali group. It's just a plus charge. Hydroxide is OH-, so that's just cesium hydroxide. So just name to formula to name. How do we break down nitrous acid? Well, nitrous, the OUS acid is telling us that this is derived off of an ite ion. So an ite ion was neutralized with H+. And so which ite ion would be nitrite? So what's the formula of nitrite? Is NO2-. Now to remember nitrite, I might have to remember nitrate is NO3-. So I just dropped 1 O off nitrate. And then I've neutralized this with H+, so it goes HNO2. So just 1 hydrogen's needed for the 1- NO2- ion. So just HNO2. Now, in terms of hydrocarbons, we go like methane, ethane, propane, butane for 1 through 4 carbons. And then after 5, or at 5 carbons, we go penta, pentane, hexa for 6, hexane. So we pick up that penta to deca nomenclature at 5 carbons. So at 4, we just have to memorize that C4H10 is butane. So with 10 hydrogens, that would be butane. So we have 4 carbons, all saturated with hydrogen. So we get CH3, CH2, CH2, CH3. That's how we get the count of 10 hydrogens. Let me rewrite that. That was pretty messy. This should be H10. And so if we drop a hydrogen, replace it with a hydroxyl group, that's the alcohol. So this would be butanol. So we have methanol, ethanol, propanol, butanol, and then just picking it from penta, pentanol, hexanol, heptanol, etc. And the only real tricky part is just getting that hydrogen count kind of to make sense. So we're just replacing one of these positions, any of them with the hydroxyl group, just one of them, and then all the others just have hydrogen. So hydrogen and all the others. There's a numbering system you don't need to know about, so don't worry about naming 1 versus 2 butanol. Just worry about spotting what butanol is and writing its formula. We have aluminum 3+. That's the only charge aluminum has. Carbonate is 2-. And so this just looks like aluminum carbonate. Good news, you don't have to spell on the test. It's all multiple choice on the nomenclature side. So you don't have to worry about typing out names where you have to worry about spelling hard to spell elements. Boron trichloride, that looks like the system we use for molecular compounds that are binary, 2 elements. So we're just picking up 1 boron and then 3 chlorine. So BCl3, Nonane is the C9. Nona is for 9. That's maybe the trickiest of the C5 to C10, is that Nona is 9, and then the hydrogen count would be the tricky part. Now, we do have a formula, 2 times the number of carbons plus 2, so that'd be 2 times 9 plus 2, that would be 20. Now, you could also figure that out by going CH3, CH2, CH3, and then we just have 7 of those CH2s in the middle. So it'd be 7 times 2 is 14, plus 3 to get to 20. So a lot of different ways that you can get this number 20. You can memorize that the saturated formula for hydrogen is 2 times the number of carbons plus 2. That's a weird thing to memorize. You can easily sketch out what this looks like too if you need to go 9 carbons, 3 on the ends, 2 hydrogens in the middle. A lot of different ways you can figure that out. Now, we see a few problems that could appear like this variety in nomenclature where we're told aluminum oxalate has a formula of Al2C2O4 What's the formula of iron 2 oxalate? So you may say, well, oxalate's not in our nomenclature. We've never, I may have mentioned it before, but I didn't put it on the list of things you have to memorize. But you don't have to have it memorized here because it's giving you the information to deduce. Really what we need to know is what's the charge of the C2O4. So from knowing that aluminum's only ever a +3, that's the big thing we just need to know is aluminum's charge can only be a +3 in an ionic compound. And so that makes the +6 the total charge from the 2 aluminums. And so the -6 is the charge that the 3 oxalate ions have to bring forth. There's 3 of them, so that makes their charge individually be -2. So the C2O4 ion has a 2- charge. That this must be what oxalate is what we can deduce from the information in the problem. So we can give you information on other ions done on your charts that you can deduce from the nomenclature system. We could have said a lot of things like, what's oxalic acid? It'd be H2C2O4. We could say, it probably wouldn't really be this formula, it probably doesn't really exist. But if we said, what's oxalite? Oxalite would have 1 fewer O. Now, I know that doesn't really exist, so we probably wouldn't ask you to name that. But if you apply the system of just losing an O from the formula, that would be what you presume the name of oxalite would be. We just change ate to ite, we just lose an O. Now, this example here just says, well, what's iron 2 oxalate? Well, we put an iron 2+ ion here, then they pair up just 1 to 1, so it'd be FeC2O4. So it's all about just deduction, applying the rules of nomenclature. So having this systematic understanding of nomenclature is useful because then we can apply and name things if given information. Breaking down protons, neutrons, electron counts for an ion here. We have a 127I- ion. And so now this is our mass number here. The mass is what's carried predominantly from the sum of the protons and the neutrons. So this is the number of protons plus the number of neutrons. So summing those particles up is where the mass comes from in our atom. That's why it's the mass number. Now, we're not told in the problem, we're not given that atomic number subscript before the I. It's because we could look it up on a periodic table. It'll be on your periodic table too. You get a periodic table that will list, the masses, the atomic number, the symbols for the elements. It just doesn't put the name of the elements, but iodine, element number 53. So this, of course, is our atomic number. And that's the number of protons in the nucleus of the atom. So iodine has 53 protons from its atomic number. It would have the difference from 127 and 53. So I take 127 minus 53. That's 74 neutrons. Now we're counting here, so sig fig rules aren't applying, right? We're not even thinking sig figs on this math because we're counting particles. These are precise numbers. It's not like the rounded number of particles. This is the exact precise number of particles these atoms, this ion would contain. And then to get to the negative charge, we've added 1 extra electron to get to an overall negative charge. So we've added 1 electron to the proton count, so we should have 54 electrons. So more electrons, more negative particles, net negative charge. If we take electrons away, we get net positive charge, like for sodium plus or magnesium 2+. So we should be 53 protons, 74 neutrons, 54 electrons. And I think this is maybe there's one more question after this, but we're getting towards the end of the packet here. I'll perform the calculation indicated, report the answer to the proper number of sig figs. This is an old question from probably 10 years ago. I almost remember the semester and the students being a little upset afterwards. Now 20 plus 1163 is hard to interpret here. And the hard part to interpret is, well, why would 1163 have been measured somehow to the nearest 1 centimeter, but the 20 only to the nearest 10 centimeters? What you have to imagine in a problem like this is we're just trying to interpret numbers, not think too much about where they came from. So presumably we use a better ruler on whatever we were measuring to get the 1163. And then remember that one day we showed the different scale markings on a ruler can impact how well we can know a number. So for some reason, somebody measured 20 just very imprecisely. And so when we did this math here first, before we do the multiplication step, I need to round to that placeholder of the 2 placeholder in 20, because I'm assuming 20 just has 1 sig fig. Now why? Who knows? It's just a different tool was used to measure the numbers. So just interpret the number 20 to have only 1 sig fig based off what we know. In this problem, we don't know anything, we're not told that that 0 is significant. We would need a decimal place. We would need it to be written 2.0 times 10 to the 1, some way to show us that that 0 is significant. Since we're not told or it's not written that way, then we're assuming that's just 20 with 1 sig fig. And so that limits our math here to be 1183 centimeters to have just 3 sig figs. Now, whether we round or not, we shouldn't necessarily round. It's probably better not to round here. But the question is just then asking, well, how many sig figs does the result have? Well, let's just look at this subtraction here. I take 15.0 and I subtract 0.00863. I'm going to round that to the greater value placeholder. And again, I'm just looking from left to right, the further to the left placeholder. So I'm going to round that result to here, which is going to keep all 5 digits being significant. Let me just write that out. So it would be 15.160 minus 0.00863. 15.151 and then 37. And so if we're reporting just that answer, we'd report it as 15.152 to 5 significant figures. For this problem, it's good enough just to note that that's 5 sig figs. And so this number here should be reported with 5 sig figs. So then when I go 5 sig figs and then times the result of the next summation with 3 sig figs, the end result gets reported to 3 significant figures. So now a few caveats here, a few thoughts. One, when you see multiplication in the problem and you see a number that has 1 sig fig, that doesn't necessarily make the result 1 sig fig. So we couldn't just simply look and say we're multiplying somewhere in this problem. One of the numbers has 1 sig fig, so the result must have 1 sig fig. Not true. We just have to apply those rules sequentially. When we apply 1163 plus 20, we only end up with 3 sig figs. If you mistakenly thought that had 4 sig figs, you might have been thinking this answer would have 4 sig figs, but it only has 3 because 1183 would only be reported to 3 significant figures. Try to round at the end. What that would mean is note that 1183 has 3 sig figs, but keep it 1183, do the next step, keep the 7 digits in the next number, and then round that final result to the 3 significant digits. So with that, let me take one last chance. There could be a lot of questions still on chapters 1 through 2, but midterm 1, just over chapters 1 to 2. I sent the video out from the other review that Dr. Chafin held on Friday. Hopefully that was a good review for you guys. But you can check the video out if you didn't get a chance to see that yet. There's a bunch of materials on Carmen. I'll probably assign the exam to take tonight just to make sure everyone sees it pop up in Carmen. But if you haven't taken the practice exams yet, make sure to take a look at those. I think they're good as a final kind of preparation, give you a good chance of what to spend maybe tonight as a last check review on some topics. If this material is coming to you really easily, just remember chapters 3 and 4, we're going to pick up the pace. Material is going to get harder as we progress in the class. If you find this to be really hard, let's kind of then think, well, what do we need to do, to prepare for chapter 3 and 4 more over the next 2 or 3 weeks, as opposed to the weekend before midterm 2, looking ahead to, beyond midterm 1. Okay, so with that, any final questions I can take today? Because we're going to get a start here on chapter 3. And like I said, there's a few aspects of chapter 3 I think that, pressing forward will help us understand about chapters 1 through 2. So some of the aspects of chapter 3, in particular when we get into the mole, when we get into what that means, how that corresponds to mass and AMUs, kind of hopefully will help us make sense of what atomic mass units are. Okay, so what chapter 3 gets into are reactions. So the main topic of chapter 3 are chemical reactions. So it's going to get into the very basics of balancing reactions. We'll talk about a couple patterns of reactivity where we can predict some products of reactions. We'll get into formula weights, Avogadro's number, the mole, which is probably categorically speaking the one concept that students have the fuzziest understanding of that I actually think is a really easy to grasp concept. So hopefully we can make sense of the mole and be running and using what the mole is in a lot of problems throughout this class and even beyond this class. Then get into, how do we find formulas? So the middle part of chapter 3 gets into, well, how do you determine formulas from experimental data? I think this is a really useful topic because it gets into, well, how do we ever determine the formulas of all those things that we were just naming in the, chapter 2? And a lot of it is from some type of experimental analysis. So we'll talk a little bit about some of those experiments, like mass percentages. You might remember some of these problems from before, but we'll talk about some of the problems that are used to determine things like empirical formula and molecular formula. There's a topic we'll mention when we get to it that we're not covering out of chapter 3. So they'll be in the middle of the notes. There's a problem actually that I show you the problem so you can see what it looks like to know that when you see it in the textbook, that you can ignore those problems in the textbook. And then towards the end of the chapter, we get into really the meat of chapter 3, which is the really useful part, something that you're going to use really, a ton throughout your chemistry classes, is stoichiometry, sort of quantifying aspects of chemical reactions, calculating how much of one reactant you need to react with the other, how much product you get, what's the yield, what's the percent yield. You might remember some of those topics. If not, of course, we'll review them. But you're going to use stoichiometry, later in this class. You're going to use it in Chem 1220. You're going to use it in OChem. You're going to use it basically in probably every chemistry class you ever take. And it's probably going to be the one concept that becomes second nature to you pretty quickly, hopefully. Okay, so let's talk about some basics of chemical reactions. And we've already written a couple reactions throughout the class, but let's sort of think about the important things that we indicate and what the meanings of some of these things are within the way we write reactions. And so we're going to start with that reaction of hydrogen and oxygen. That was the balloon that we exploded earlier in the class, had H2 and O2, and the spark allowed the elements to recombine to form water. And so we had H2, and it's a gas, so we usually indicate the physical state of the substances. Now, we don't always know how to predict, so we might write the physical states for a lot of different things in reactions. You may or may not always be able to predict those physical states for every substance that you ever see within a reaction. So then O2 is the other reactant, and then we'd be writing the product or forming water. In the context of the reaction that we perform, we blow up that balloon. The water floated away from the fireball as water vapor before it had a chance to condense. Again, that's an example where, is that water gas, water liquid? You don't always know. Just in the example of the reaction I'm writing, I'm just using water in the gaseous state here. So the idea is your reactants and products generally will have a physical state indicated, gas, liquid, or solid. We'll pick up the AQ tag in the next chapter. You may have seen aqueous. We'll use that tag when we get to chapter 4 and talk more about that later. So we're just indicating, our physical state here in parentheses. And then this reaction here wouldn't be balanced. We don't have the proper number of atoms on the left and right side. As written, it appears as if we're creating and destroying atoms. In this case, it would be, destroying an oxygen atom. So let's go ahead and put a 2 in front of water. That gives us 2 oxygen atoms on both sides of the reaction. And then that gives us 4 H atoms, so I need not 4H2, but I need 2H2. So I use coefficients in front. So coefficients in front of the reactant are just indicating the relative quantities of hydrogen to oxygen. So I have 2 parts of hydrogen to 1 part of oxygen, meaning that I would just have an H2 molecule. So let's have hydrogen be the shaded sphere, oxygen just be an open sphere. It's kind of weird for O. It's just O will just look like the O atom, so O will just be an open sphere. So we have H2, we'll just have 2 of them. And then we'll have an O2. And then we're just going to recombine, break that O2 in part, and wedge it between the 2 hydrogens to make 1 water. And again, we're not going to think about the 3-dimensional shape yet of what water really looks like, so we'll pick that up later. And we just do it again. So we take the other O, wedge it between the other hydrogen. And so just getting at fundamentally what a reaction's getting at is what was present before, what's present after. The book likes to call reactions equations. I don't like that nomenclature, but the book calls a chemical reaction a chemical equation. The reason why I don't like the equation is I'm not saying 2H2 plus an O2 is equal to 2 waters. I'm just trying to say here that this is the before, what's present before the reaction. This is what's present after the reaction. So it's just a before-after. So what do we have there before? What does it change into after the reaction completes? It's trying to show us that net change that's taking place throughout the reaction. And so the coefficients are just relating to how many are there. So there's 1 water, there's 2 waters, so that's why I write 2 here. If, writing H, like imagine if I said to balance this reaction, why not write H4O2? Well, H4O2 would be indicating that I would have a molecule that would have 4 hydrogens and 2 oxygens. That's not what we have here. We have 2 distinct molecules of water being formed from 2 distinct molecules of hydrogen reacting with 1 distinct molecule of O2. Now, you kind of can see the need for something like a mole unit. If I looked at an actual container, or looked at that balloon that we blew up, there were millions upon millions upon millions of H2 and O2 molecules present before the reaction, obviously millions and millions and millions of water molecules that were produced. So we're going to need a different unit so we don't have to count out reactions on the millions plus millions plus millions of scales. And it's really, on orders of more like 10 to the 22 to the 10 to the 24 actual molecules that were present. So huge, huge quantities of actual molecules are present. So we're going to need to think maybe small scale, like at the atomic level, to try to see what's going on at like an atomic perspective, and then think globally at a bigger picture that's going to get us towards that mole unit using Avogadro's number. Now, for this part here, let's just look at a few general types of reactions that we'll see, and then within them, just make sure we understand how to balance the reactions. And so a combination reaction is anytime you take 2 or more things, combine them into a single product. And the single product, there might be more than one of it just by balancing. So NaCl is a good example. We can form sodium chloride from sodium and chlorine forming from their elemental forms. So the sodium exists as a solid. Chlorine, again, this may not be something you can predict automatically, but something that might be worth pointing out is, like our periodic table shows us too, F and Cl are the gas-shaded atoms. So the atoms in red are gases at room temperature. The atoms in blue are liquids at room temperature. I think it's nice to point out that there's only 2 liquid elements at room temperature. Bromine's one of them. Mercury, of course, is the other. So those are the only 2 elements in the periodic table that are liquids at room temperature. Cesium is close, though it's hard to... Cesium, there's not a whole lot of it on Earth, but its melting point is just beyond room temperature. Cesium's melting point's like 30 degrees C, so it almost was a liquid at room temperature. If room temperature was like 35 degrees, cesium would be also a liquid. And then I think it's gallium is also close to room temperature. So gallium's melting point, I think, is right in that ballpark of like 30 to 35 degrees C. So there's a couple elements that are close that you can melt. The temperature is relatively close to room temperature, but the 2 main elements that are liquid at room temperature, mercury and bromine, and then we then go to iodine being a solid. So I2 is a solid. Just sometimes it's useful to know that. And we'll try to talk even later in the class why that might be. So F2Cl2 gases, Br2 liquid, I2 solid. Again, not really telling you that so you memorize that, but just so you can see the nonmetals can still be liquids and solids at room temperature too. Okay, so when sodium combines with chlorine, we're going to make 2 NaCls by balancing just to get 2 chlorines on both sides, and so then that kicks us to have 2 sodiums. So we can take 2 different elements combine, or 2 different substances, combine them into a single product, even though, of course, there's 2 of the products. That doesn't change this off of being a combination reaction. So we have a combination reaction for sodium and chlorine. Al and O2 react to form their common ionic compound of aluminum 3 plus, O2 minus, so Al2O3, aluminum oxide. And so the balancing here, how might we balance this reaction? Well, once I see 2 versus 3 O's, I'm going to probably just start by doubling would be the first starting point. I would think, well, if I double the Al2O3, at least makes the O count even. So then I can put now 3 for oxygen to have 6 O's on both sides. So I'm just trying to make sure 2 times 3 gives me 6, 3 times 2 gives me 6. That puts the oxygens into balance. So balancing is just a little bit of trial and error. Just when you see even odd pairs, just double something and then see if it works. If not, double the other thing, see if it works. If I double the O2, it would give me 4 O's. If I tried just doubling over here, I would have had 4 O's that I wouldn't have been able to balance on the product side. And then I have 4 aluminum, so 4Al. So balancing is usually not a sticky point here, but balancing is just getting the same number of atoms, same count for each element on the left side versus the right side. So just give me the snapshot before and after the reaction takes place. Now, a decomposition reaction is where we take a single reactant and turn it into 2 or more products. So an example of that are things like carbonates that are heated. Usually you heat these up like in an oven, and then the CO2 gas kind of falls off of the carbonate formula and leaves behind the oxide ion. So you go from CO3 2 minus to an O2 minus. You're just losing that neutral CO2 molecule off. This is actually an important step in making cement. So cement, you take carbonates that you mine from the earth, heat them up, lose the CO2, make the oxide, in water. You can then deliver the oxide to where you need it, and then as it dries, it then goes back to the oxide form. And so anyways, like these carbonates and oxides are present within cement and are used in some everyday tasks. And so carbonate flies off of this reaction here. The use of things like calcium carbonate, where it's heated to make calcium oxide for cement, is actually a source of CO2 in the atmosphere. So it turns out if you use cement, you actually had put CO2 into the atmosphere. So if you think of human sources of CO2 in the atmosphere, it's not just cars, it's also airplanes, it's also cement. There's a lot of different things that use and produce CO2 in a man-made form into the atmosphere. Okay, and so the balancing is just 1 to 1 to 1 for all these things here. If I have a more complicated example, like I have here iron 3+, how do I know that's 3+? Well, it's just I'm almost taking these charges back. I know carbonate's a 2 minus, so that's a 6 minus here. So we're hopefully reinforcing some nomenclature and can identify that would be iron 3 carbonate. Now, iron 3 carbonate is going to decompose to give off now 3 CO2s because I have 3 carbonate ions. So I get 3 CO2 gases given off here, and that's going to leave behind Fe2 and then O3. It's going to leave behind the 3 leftover oxygen atoms as oxide ion. So we had CO3, 3, so now I just have O3, and I lost the 3 CO2s. And so then if I need to name this, this would be iron 3 oxide. And then that would be balanced in like the 1 to 1 to 3. So 1 iron 3 carbonate goes to 1 iron 3 oxide plus 3 CO2s. And you can double check. There's 3 carbons on both sides. There's 6 O's here plus 3. That's 9 O's. There's 9 O's here. 2 irons and 2 irons. So you can always double check the atom counts on both sides if you want to make sure. And now the last category of reactions, one that we have predictive capabilities on this reaction pretty easily. Hydrocarbons combust. When they combust, they form CO2 and water. So if we take something like methane, burn it in the presence of oxygen, then we produce carbon dioxide and water vapor. Now the balancing here, maybe the hydrogen counts the easiest starting point. So if I go 2 waters here, balances the hydrogen. Then I have 1, 2, 3, 4 O's. So I need 2 O's here to give me 4 O's on both sides. If I, at this point, need a fraction, generally you shouldn't have fractions in a properly balanced reaction. If you find that you have to use like a half in front of O2, then just double all the coefficients to get rid of the half, or just kind of keep going with your balancing until we get whole numbers on both sides. And then 1, we generally don't write the 1 in front, but we have 1 in front of CH4 here to put it into balance. So 1 carbon on both sides from 1 CO2. We have 2 oxygens on both sides, so 2, that gives me 4 O atoms on both sides as well. Now we can also combust things like ethanol. Ethanol will burn, so don't try to fireball a vodka shot unless you want to catch your face on fire. So don't play around with trying to burn like alcohol in parties or whatever, but alcohol will burn just like most hydrocarbons do. And then it will form CO2 and water just the same way. And so if we start balancing maybe the hydrogens here, so we have 6 hydrogens, so that would be 3 waters. And so that's, we need 2 CO2s to balance the carbon. So that gives me 2 carbon atoms on both sides. And so right now my oxygen count on the product side would be 7, 4 plus 3. And now on my reactant side, I have 1 here. So then I only need a 3 here. So 1 ethanol brings 1 O atom, and then 3 O2s brings the other 6. So here I have 7 O's over here as well. So So again, just balancing the atoms on the elements on both sides of the reaction, so we're not creating or destroying mass through that chemical reaction. There's an important topic to talk about here that's useful to know and just to be aware of. Well, what happens if we don't have enough oxygen? Like, we talk a lot in this chapter about, well, if you run out of a reactant, then the reaction just stops and you get an excess reactant. You guys probably remember these problems. Maybe you don't remember how to solve them, so we'll show you later in the chapter. But do you remember the concept of that problem of you have two reactants? If you run out of one, the reaction stops and then the other is just left over in excess, right? Well, if you run out of oxygen in a combustion reaction, you'll actually produce a different product. It's one of the few reactions that just will change the nature of the products. And do you know what that product would be? I know he knows it. Yeah, carbon monoxide. So if you have a clogged air filter on a combustion source, like if you have a natural gas heater at home and you have a clogged air filter, that's where your oxygen is coming from, is from that oxygen supply, then you might have a limiting amount of oxygen. And if you don't have enough oxygen, you can produce carbon monoxide in a combustion reaction. This is useful to know because carbon monoxide is a deadly poisonous gas, and it will make you feel foggy and kind of like you're sick. It'll make you feel like you have the flu and you're just foggy on what's going on, make you really tired, and you'll end up probably dying if you don't get the fresh air before you succumb to the condition of carbon monoxide poisoning. So it's really hazardous because, in fact, there's been stories of people who will call their relatives and say, I'm just not feeling well. Or feeling really I just don't understand what's going on. I just feel like maybe I had the flu coming on, and then they find them dead from CO poisoning the next day because they just didn't realize what was going on. It's almost like being drunk in a way. It kind of makes you feel. Another place this comes up is let's say your car crashes or something, and it's winter, so it's cold out, so you're waiting for the tow truck to show up. You're sitting in your car with the heater on. Well, your car is an internal combustion engine, unless it's an electric car. But if your car has a gas engine, you put gas in your car, and the exhaust has a hole in it because maybe your car just crashed, so the tailpipe has a crack in it now. It could be putting those fumes up into your car. People have died from carbon monoxide poisoning waiting for the tow truck to show up. There was a story just over 10 years ago in Marysville, Ohio, where that happened, where two individuals were killed in that sense. So I just want you to be aware of this. Every now and then there's cases where chemistry is useful and it's applicable and can teach you something, and that is make sure your furnace filters are changed. Make sure if you have a combustion engine in your home in the form of some sort of furnace that you have a carbon monoxide detector. If you're in the dorms, everything's forced air and so there's no real natural gas usually in the dorms and things like that. But if you're in your own apartment, if you're at home, might be something to worry about. In your car, something to worry about as well. So always want to give the chance to save people, or just to be aware of, even if your friends call you and they sound like something crazy is going on, be like, get the fresh air. Every now and then it may be a good idea too. If you're not sure, just get the fresh air, yada yada. I'll quit preaching about carbon monoxide. Hello, I forgot to record on the slide in class today, so this is me back in my office kind of re-recording on this particular slide. So we're told here that 1 mole is defined as this number, 6.022140076 times 10 to the 23, which is the number of atoms in a 12.000, etc. gram sample of carbon-12. So the way this kind of goes is you can refine a sample of carbon, which of course would contain mostly carbon-12 and 13, tiny fraction of carbon-14. So you try to purify that sample to contain just carbon-12, and you do that to 99.9999 to 9 or 10 digits of precision. And so they very, very precisely came up with this carbon-12 sample, and then they counted the number of atoms within the sample very, very carefully and precisely, and they determined that number of atoms is what we're defining to be this special number of Avogadro's number. And so we define this number here to be n sub a, we call that Avogadro's number. Now, the way this kind of can go is that this is, the number of carbon atoms within a 12 gram sample. And so you can determine here and kind of link, determine the mass of 1 atom in grams. So if I just divide both sides by that number of atoms, so let's call this x here. So divide both sides by x, divide both sides by Avogadro's number, and then you come up with the mass that 1 carbon-12 atom has a mass of 1.99264688 blah 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 times 10 to the minus 23 grams. A really, really small mass, of course, for one single atom. Now, the precision here is just trying to show you that we're being very, very careful, or that the scientists are being very, very careful and having a very precise mass sample known to contain, mostly, if not all, carbon-12, and then carefully counted those number of atoms. And so we're just trying to show the degree of precision due to the importance and relevance of this number. And so then this mass here was set equal to the mass of the carbon-12 atom with 12 AMU, because if you recall, that's how we define the AMU scale, is off the mass of one single carbon-12 atom. So one carbon-12 atom has a mass of 12 AMU exactly because it's defining and setting up this AMU scale. So now divide both sides here by 12, and you come up with the conversion that 1 AMU is equal to that number of grams. And so I'm just throwing this in my calculator. So 1.99264688 times 10 to the minus 23, divide by 12. And so we get 1.66053907. Again, just trying to show that we can be really precise here with this math, since these numbers are really well characterized. And I'm just trying to show you that later you'll get back to Avogadro's number very precisely too. So we'll see that in a moment. And so this tells us how many grams there are in an AMU. So an AMU of anything, 1 AMU is just a conversion factor into grams. So it doesn't matter what the thing is. AMU is just a simple conversion factor into grams. And then one other thing we can do is, well, let's call this number here, let's call that x. Now let's divide both sides by this new x here. And so let's more or less invert the conversion so we can figure out how many AMU there are in 1 gram. So if I invert this answer, we get 6.022140076. So we have an Avogadro's number of AMU in a gram. We also have an Avogadro's number of atoms in the mole. So 1 mole of anything is just this Avogadro's number of the thing. So we did this example in class. So we had 1 mole of helium would be an Avogadro's number of helium, and helium's an atom, so it's an Avogadro's number of helium atoms. 1 mole of H2 would be 6.022 times 10 to the 23 H2. H2 is a molecule, so H2 molecules. If we have 1 mole of CH4 for that compound, you'd have 6.022 times 10 to the 23 CH4 molecules. And then in terms of total atoms, we'd have, total atom count here. We'd have 1 times Avogadro's number for helium. We'd have 2 times Avogadro's number because there's 2 atoms of hydrogen per 1 molecule. We'd have 5 times Avogadro's number in the case of CH4. Okay, so the moles, it's like tricky to see how it's defined here because it's hard to imagine how these experiments were done, but we just experimentally count the number of particles in this precise mass sample and then define the AMU scale off that same atom's mass and anchor that AMU scale. And so the utility here is that, and we kind of saw this hopefully through an example we'll pick up and restart from the class on Wednesday, that if you're thinking of a molecule, if it has a molecular weight in AMU, it's going to be the same number in grams per mole. So we'll hopefully see and be able to use AMU scale or like mass scale, grams per mole scale numbers in problems. So this slide here is just working through the math on the previous slide. So just again showing that 12 AMU corresponded to the mass of that 1/8 of the 1 carbon atom. So then we just divide both sides by 12. That's how we get this AMU to gram conversion. And then if we call this x, if we divide both sides by x, and then we get the gram to AMU conversion. So we usually give you like the AMU to gram conversion if you need it on a test, but it's a really easy conversion because it's just an Avogadro's number of AMU correspond to 1 gram. Now let's try to do a couple problems just so we can try to like imagine like how this is used and then get some vernacular with this. So a molecular weight is usually what we think of in AMU. So if I ask for molecular weight, it's usually kind of thinking what's the weight of like one molecule on average. That is usually what we think of in AMU units. We could also talk about molar mass, which is the mass usually in grams per mole of the substance. And so let's look at C2H2, so acetylene. And so what we do is just take 2 times the mass of carbon on average from the periodic table, so 12.01. Now, you could go as precise as you need to for an example. Usually I go to about 4 digits is usually what I'm trying to write for a number. I usually go to the nearest, like 100th place when, it's in the tens value. You'll pick up how, like, the number of digits that are useful. You could go 12.0 is probably okay, but I like to usually pick up 1 extra sig fig. So I'm just looking at the periodic table for carbon. 2 times to get 4 sig figs for hydrogen, I go to 1.008. Not a big detail, but I think it's just good to sort of be precise. And if you do a lot of examples with like hydrogen, carbon, nitrogen, you're going to memorize a lot of these atomic weights as you do examples. And so then we're just going to add these all up. And so again, you could look up more precise, but usually we're going to give our formula weights to the nearest, roughly like 4 sig figs is probably good enough for most problems in lecture. In lab, you might need to look atomic weights up a little bit more precisely. If you have a mass to like 5 or 6 significant figures from your balance in lab, you might need to pick up a couple extra digits on your atomic weights for lab examples. So just doing this works out to be 26.04 AMU. Now this is actually another important question. What units do you throw on here? Because like AMU is like our atomic mass unit masses that we were thinking from our average atomic weights out of chapter 2. When I look at the periodic table, I'm usually thinking AMU. And so this is the mass of one molecule in units of AMU. If I said, well, to compare the mass of one molecule in grams versus AMU, like down here, let's deal with this question first and then think about our gram per mole conversion second. So the mass of one molecule of C2H2 in grams is going to be really, really small. Like one molecule is extremely tiny. And so the number of grams for one molecule's mass is 26.04 atomic mass units, AMUs. Well, that AMU conversion was Avogadro's number, and we're dividing by Avogadro's number. So 6.022 times 10 to the 23 AMU per gram. So 26.04 is the average atomic weight of a molecule of C2H2 in atomic mass units. If I take 26.04, 6.022 e to the 23, 4.324 times 10 to the minus 23 grams. That's pretty small. That's not much mass at all. But that's just showing you that one molecule's mass, very, very, very incredibly small. And so 26.04 AMU, whole number size, but that's just the average mass in that AMU scale for the molecule. Now, what about in grams per mole? It's going to turn out to be the exact same number. 23.04 is going to be the answer in grams per mole. There's a few ways we can get there. One is that if you just do one more conversion onto this scale here, if you take this problem here and just do one more problem and say that this is the mass per molecule, and then all we need to do is the conversion into moles. So the only thing we need to multiply by is the molecule to mole conversion, which is Avogadro's number. And then the molecules cancels. And then you get your mass in grams per mole. And then we multiplied by Avogadro's number, then we divided by Avogadro's number. So it works out to be 26.04 grams per mole. I hate that my pen is being slow, but the idea is your molecular weight in AMU is exactly the same as the weight in grams per mole for everything. We'll highlight that at the start of class on Wednesday and move forward from here. Good luck on midterm 1. Hope it goes well for everybody. I have office hours later today. Yeah. What's that? Oh, lecture quiz for today. I never got to it. I will EX it for everybody. That's not, like, so yeah, I didn't get the lecture quiz today. I'll just excuse everybody in the class for today's attendance. But thanks for being here. It was really useful to be here today.